Welcome to Sleepy Stories, where curiosity and calm meet beneath the same sky. Here, knowledge unfolds slowly, like the turning of planets, and you can drift into rest while your mind continues to learn. If sleep comes quickly, let it. If not, let the rhythm of quiet explanation carry you. There is no hurry. The universe moves at its own pace, and tonight, we will move with it. If you enjoy drifting through stories like this, a like or subscribe helps us keep creating more sleepy stories for curious minds like yours. There is something strange holding the universe together. You cannot see it. You cannot touch it. You cannot point to it in a night sky or scoop it into a laboratory jar. And yet, without it, galaxies would fall apart. Stars would drift loose like leaves on a forgotten wind. You would not be here. I would not be here. Nothing familiar would be here at all. This invisible something has a name, dark matter, but names do not make things more visible. They only mark the places where mystery begins. For a long time, scientists thought they had most of the universe figured out. Newton gave us gravity, Einstein curved space and time. Hubble told us the cosmos was expanding, everything elegant, everything in motion. But there was a silence between the stars that equations could not explain. When astronomers looked at galaxies, they noticed something unsettling. The stars at the outer edges were spinning far too quickly, as if held by an invisible hand. According to physics, those stars should be flung into space like sparks from a wheel. But they weren't. They stayed. They circled. They obeyed a gravity that couldn't be accounted for. The mass we could see, stars, gas, dust, wasn't enough. It was like watching a swing sway without wind, or a boat move without a paddle. Something else was at work. That something, scientists now believe, makes up more than 5 times as much mass as all the visible matter in the universe. 5 times more. Yet it does not shine. It does not glow. It does not announce itself in any obvious way. It is present only in effect, in pull, in persuasion. Imagine a great ballroom with dancers spinning in elegant arcs. The room is dark, you cannot see the walls, you cannot see the floor, but the dancers move in patterns that suggest the space around them. They never crash, they never drift. Something shapes their path, something unseen. This is how dark matter enters the story, not through appearance, but through influence. Its role is silent, but its presence is loud in the data. The universe doesn't just allow dark matter, it depends on it. And so we begin here, at the edge of what we know, looking not for light, but for the shape that light cannot show. Listening not for noise, but for the gentle distortion of orbits and clusters and curves that suggest a deeper architecture. It is a strange kind of knowing, like learning someone exists only by watching how others change when they enter the room. Dark matter is not the darkness of shadows. It is the darkness of absence, a structure made of silence, a weight without a surface. And yet, it surrounds us. It holds galaxies like hands. It gives shape to emptiness. As we move deeper into this mystery, let your thoughts rest in that idea, that what is most powerful may not be what shines brightest, but what holds everything quietly in place. There's a quiet discomfort that sometimes arises in science, not from what we don't know, but from what we thought we already understood. For centuries, the laws of gravity seemed absolute. Newton described its force. Einstein reshaped it into curves in space and time. From apples falling to Earth to planets circling stars, the universe behaved exactly as expected. Predictable, beautiful, balanced. And then came the galaxies. Spiral galaxies, like our own Milky Way, spin. Their stars swirl around the center, like dancers in motion. According to the rules of gravity, those closer to the center, where most of the visible mass lies, should move faster. Stars on the outskirts, far from that center of mass, should orbit more slowly. It's the same logic that keeps the outer planets in our solar system moving at more leisurely speeds than Mercury or Venus. But when astronomers measured the rotation of galaxies, they found something deeply unsettling. The stars far from the center weren't slowing down, they were moving just as fast as those close in. The rotation curves, Those neat graphs that should have dropped off, flattened out instead. It was as if the rules had been rewritten when no one was looking. The math no longer added up. If visible matter were the only source of gravity, galaxies should be tearing themselves apart at the edges. But they weren't. They were holding together, spinning in defiance of known physics. Something unseen was providing the missing gravitational glue. It was a turning point. A moment when the universe whispered, "There is more than meets the eye." You can think of it like this. Imagine watching children on a merry-go-round. The ones in the center spin tightly, quickly. The ones near the edge should lag behind, pulled less by the center's force. But here, they don't. They stay perfectly aligned, as if some invisible hands push them onward in perfect sync. That invisible hand, scientists realized, must be something else, something more massive than all the stars and gas combined, something that does not shine, but exerts force, something that behaves like matter, but refuses to be seen. Dark matter. It wasn't a single experiment or observation. It was a pattern, repeated across galaxy after galaxy, decade after decade. No matter where astronomers looked, the results were the same. The stars were spinning too fast, and the universe was holding its breath. And so, a new kind of matter entered our models. Not because we found it glowing in the sky, but because the sky behaved as if it were there. It's worth pausing here. Not every discovery begins with a flash of light. Some begin with a discrepancy, a question mark, a quiet rebellion against what we thought we knew. Dark matter began not as a new thing, but as an absence, an unexplained remainder in the equation of the universe. In time, that absence would become a presence, and that presence would reshape cosmology. Let this moment settle. The universe doesn't always show its hand. Sometimes it leaves clues in motion, in imbalance, in things that spin when they shouldn't. And in those patterns, we begin to see the outline of something far greater than we imagined. Something that doesn't add up until you realize it's what holds everything together. Gravity is a quiet storyteller. It speaks not with sound, but with the slow, inevitable motion of everything that floats in space. It does not flash or shout. It pulls, always inward, always gently. It sculpts the dance of planets, the spiral of galaxies, and the flight of comets that arc through centuries. It shapes the very structure of the cosmos, patiently and invisibly. And it was gravity that first told us something was missing. We didn't find dark matter because we saw it. We found it because gravity behaved as though something else was there. An uninvited guest at the cosmic table, silent but heavy, reshaping everything around it. Astronomers watched stars moving faster than they should. They saw galaxies clinging together when, by all rights, they should be drifting apart. They observed light bending where no visible mass existed. Gravity was reacting to something unseen. In physics, this is no small thing. You can lie about your appearance, you can hide from light, but you cannot fake gravity. Einstein showed us that gravity is not a force, strictly speaking, but the bending of space itself. Mass bends space, and objects follow the curve. That means wherever we see space bending, something with mass must be doing the bending. When we look at distant galaxies and see the light from even more distant objects behind them curve and twist, we call that gravitational lensing. And when we map where the light bends the most, we often find no stars, no clouds, no dust, nothing visible at all. And yet, the lensing is real. The light has curved, space has bent, and something has done the bending. That something is dark matter. To see it, we look not at the thing itself, but at how everything else reacts to it. A lens made of silence, a fingerprint left in the curvature of space. Imagine you're standing at the edge of a calm lake. The surface is still. Then, without a sound, a single ripple appears, spreading out across the water. You didn't see what made it. You didn't hear the splash. But something happened. You know it. You see the ripple. Gravity works the same way. It ripples through space when something with mass is present. And in many places, those ripples tell us that there's more out there than meets the eye. This is the essence of indirect evidence. We infer the presence of the invisible by the shape of its influence. Gravity allows us to map what we cannot touch, to draw outlines of things that remain in darkness. It is a kind of astronomy that relies on shadows, not light. One of the most elegant examples is gravitational lensing itself. Light from a galaxy billions of light-years away travels through space. On its journey to us, it passes near a cluster of galaxies, dense and massive. If only visible matter were there, the light would bend a little, but the amount of distortion we observe is much greater. The light curves as though it had passed near something far more massive than the stars alone could explain. These cosmic lenses let us map the hidden. Like a detective tracing footprints in snow, we learn about what we cannot see by observing its impact on everything else. And the maps are clear. All across the sky, dark matter traces invisible webs, surrounds galaxies with unseen halos, and pulls on light as if to remind us, I am here. It does not glow, it does not reflect, it simply holds, and in that holding, it reveals. This is what gravity gives us, not just motion, but meaning, a tool to see the unseeable, a voice that speaks only when things fall, drift, or bend. And in listening to it closely, we have come to understand that most of the universe is not what we thought. Most of it is dark, not evil, not frightening, just hidden, just patient, just waiting to be felt. Dark matter isn't the first thing science has failed to see. Throughout history, some of our most important discoveries began with something that wasn't there, at least, not at first. Ideas that shaped entire centuries often started as guesses, whispers, or wrong turns. It seems we humans have always been haunted by invisible things, and sometimes we've been right to be. Long before we understood oxygen, people believed in phlogiston, a fire-like element thought to be released during combustion. According to this theory, anything that burned contained phlogiston, and burning simply released it into the air. The idea was wrong, but it made sense at the time. Observations were limited, tools were primitive. Phlogiston helped explain something otherwise mysterious. Eventually, better experiments showed the truth. Oxygen entered the picture, and phlogiston faded into obscurity, not because it was foolish, but because it was a placeholder, a name for a gap, a shadow waiting for form. The same happened with the ether, an invisible substance once believed to fill the emptiness of space. Scientists thought light, like sound, needed a medium to travel through, so they imagined a universal fabric, a kind of celestial air that permeated the cosmos. Once again, it made sense, but later, experiments proved the ether unnecessary. Light could travel through a vacuum. The theory vanished. These moments weren't failures, they were steps in the process, the human process of reaching out in the dark, naming what we don't yet understand, and refining our guesses until they finally touch truth. And now, we have dark matter. It, too, began as a placeholder, an explanation for something odd. Galaxies spinning too fast, gravitational lensing with no visible cause, clusters holding together when they should fall apart. And yet, decade after decade, the evidence for dark matter has grown stronger, not weaker. Its silence has weight, its absence is full of presence. There's a humility in this, a reminder that science doesn't always progress through sudden revelations. Sometimes it creeps forward by subtraction, by removing what can't be, until only the impossible remains. The philosopher Karl Popper once said that science advances not by proving things right, but by proving things wrong. And dark matter, strangely enough, fits that mold. We've proven again and again that what we see isn't enough. We've ruled out dust, gas, stars too faint to notice. We've ruled out black holes in large enough numbers, rogue planets, and massive objects hiding in the shadows. What's left is something else entirely. Not visible, not ordinary, but incredibly, undeniably real. To understand this moment in science, it helps to recognize the long lineage of the invisible. Electricity was once unseen magic. Germs were unthinkable. Atoms at one time were just philosophy. Each one moved from shadow to structure through patience, observation, and belief in what could not yet be touched. Dark matter continues that tradition, a quiet mystery pulling at the edge of what we know. It doesn't shout its existence, it leans in, it waits, and so the story continues. Not of ghosts or guesses, but of gravity that will not lie, of patterns that persist, of silence that speaks. This is the history of hidden things, first denied, then doubted, then accepted, not because we saw them, but because their effects became impossible to ignore. Let that settle for a moment. The idea that science, for all its rigor and reason, still walks in the dark more often than we admit. That the world we think we understand is held together by something we've never seen and may never see. But we feel it. We trace it. We name it. Dark matter is not just a mystery. It is a mirror showing us who we are. Seekers of patterns, builders of stories, wanderers in the unseen. Sometimes the truth arrives too early, so early that no one knows what to do with it. In the early 20th century, a Swiss astronomer named Fritz Zwicky was looking at something no one else seemed to notice: the motion of galaxies in a distant cluster called coma. He observed that the galaxies inside the cluster were moving far too fast. According to the amount of visible matter, they should have flown apart, but they hadn't. They stayed bound together, as if something unseen was holding them in place. Zwicky did the math. The visible mass, stars, gas, and dust, wasn't enough to generate the gravity needed to explain what he saw. So he proposed something radical for the time. There must be missing mass. He even gave it a name, Dunkel Materie, which means dark matter in German. In many ways he was right, but almost no one listened. Part of the problem was Zwicky himself. He was brilliant, yes, but also eccentric, difficult, and brash. He clashed with colleagues, dismissed critics with biting words, and carried himself like a prophet in a room full of fools. Some admired him, most ignored him. His idea of dark matter remained in the margins of astrophysics for decades. No one disproved it, but no one pursued it either. The problem of the missing mass was set aside like a strange puzzle piece that didn't fit the picture anyone else was trying to assemble. And yet, he had seen it. Long before the world was ready. Long before gravitational lensing and galaxy rotation curves and computer simulations showed us the same thing, again and again. He saw the absence, and he believed it meant something. Today, Zwicky is remembered not just for his temper, but for his insight. His observations of the coma cluster are now recognized as one of the first serious clues that dark matter exists. He couldn't prove it, but he pointed toward it, and he did so with clarity, conviction, and the kind of stubborn curiosity that sometimes changes everything. There's something deeply human in that. Not every discovery is met with applause. Sometimes it's met with silence, or worse, with laughter. Sometimes the person who sees most clearly is the one who is hardest to hear. But the universe doesn't care about popularity. It cares about gravity. It listens only to truth. And the galaxies in the coma cluster continued their strange dance, held in place by something Zwicky had already guessed at. Imagine standing at the edge of a vast swarm of galaxies, watching them orbit one another like bees in a hive. You measure their speed, their mass, their light, and then you realize what you see accounts for almost nothing. It's like hearing a thunderstorm and seeing only a few clouds. Something bigger must be hiding behind the curtain. Zwicky saw that curtain ripple. He was mocked. He was ignored. But he was not wrong. Science doesn't always move forward in a straight line. It loops, pauses, revisits. It forgets and remembers. And sometimes it takes a generation or two for the truth to be seen clearly. Fritz Zwicky didn't live to see his idea embraced. But today, the term he used, dark matter, is part of the everyday language of astrophysics. His fingerprints are on every galaxy rotation curve, every simulation, every gravitational map. Let that settle. Sometimes, the ones who speak first speak alone. But if their words are true, the universe has a way of catching up. Let your body soften. You don't have to chase understanding right now. You don't have to solve anything. Just as gravity does not rush, neither do you. There's no urgency here, only a quiet pull, like the kind that holds the stars in place. We often think of darkness as absence, but in the universe, darkness is structure. Dark matter, though unseen, gives shape to galaxies. It is the skeleton beneath the spiral. It does not glow. It does not call attention to itself. It simply holds, gently and without fail. Tonight, let that idea hold you. Let your breath be the orbit. Let your mind be the drifting star. Each thought that rises can spiral outward, slowly, like a satellite circling something it cannot name. You don't need to resist. Just drift. In the vast silence of space, stars whirl through invisible halos of dark matter. Entire galaxies are cradled by this unseen presence. They don't question the pull. They don't search for the source. They simply move within it, guided, balanced, secure. You are the same. Even now, your body is wrapped in gravity. You're held gently to this planet, without effort. No one has to remind you. No one has to explain. You don't feel the pull directly, but everything you are depends on it. You are anchored by something quiet, reliable, and unseen. The same is true for sleep. You might not know exactly when it arrives. It doesn't announce itself with fanfare. It begins slowly, like a softening of edges, like a star, long ago, beginning its spiral path around an unseen center. You don't need to follow every thought. You don't need to control where your awareness goes. Sleep is not a destination to reach. It is a gravity to yield to. Even in the dark, something holds you. Dark matter surrounds galaxies in halos wider than the eye can imagine. These halos do not shimmer, do not hum, do not touch. But they are there. They shape the orbits. They determine the curves. They are invisible and absolutely necessary. Tonight, sleep can be the same. You may not see it coming. You may not feel the moment it begins, but its shape will hold you. Its silence will cradle your thoughts. Its pull will steady the stars of your mind. Let the weight of the day fall away. Let your limbs be heavy. Let your chest rise and fall like the tide of a slow-turning world. There is no pressure now, no requirement to understand. Like the astronomers who first noticed galaxies moving too fast, you don't need to solve the mystery to be moved by it. You are already in orbit, already circling a center you cannot see, already suspended in the gentle curve of something larger than thought. If sleep comes, let it come. If it waits, that's fine too. You are drifting in dark matter now, not in fear, not in confusion, but in trust. Trust in the presence that does not need to be visible to be real. Trust in the gravity you cannot name. In time, sleep will arrive, not like a switch, but like a change in tide. You'll feel it not as an end, but as a soft continuation of this moment, where breath slows, thoughts fade, and silence becomes the strongest force of all. It began with a curve that didn't fall. Astronomers expected a certain shape, an elegant drop, like the fading echo of a bell. This shape wasn't drawn in chalk or carved in stone. It came from Newton, from Kepler, from the mathematics of centuries. A spiral galaxy, they believed, should spin like a solar system. The stars at its center would orbit quickly, pulled by the mass of the dense galactic core. But farther out, at the edge, stars should slow, just as Pluto moves slower than Earth. Instead, they found something strange. When they measured those outer stars, they weren't slowing down, they were keeping pace. They were moving just as fast as the inner ones. The curve didn't fall, it flattened. At first, it seemed like an error. Perhaps the measurements were off, the data too thin, the methods flawed, but the results repeated. Again and again, across galaxy after galaxy, the same impossible curve appeared, outer stars refusing to obey gravity as we knew it. This curve became a clue, a contradiction, and like all great contradictions in science, it pointed to something new. It's called a galactic rotation curve, a graph that plots the speed of stars at different distances from the center of a galaxy. Based on the mass we can see, the curve should peak near the center and decline with distance. But real galaxies don't behave that way. Their rotation curves stay flat or even rise slightly toward the edges. Imagine standing in a field watching a distant carousel spin. You expect the horses on the outer edge to move more slowly, but they don't. They fly just as fast as the ones near the pole, and you wonder, what holds them? What keeps them from flying off into the dark? The answer must be more mass, more gravity than we can see. This was one of the most compelling early signs of dark matter, not because it revealed what dark matter is, but because it revealed what matter isn't doing. The stars are staying in place, but the visible matter can't explain how. It's not just one galaxy. It's not just the Milky Way. It's all of them. Across the observable universe, spiral galaxies show this same unexpected behavior. The mass we see, stars, gas, dust, accounts for only a fraction of what must be there to explain the motion. Something else is holding the stars in orbit, something massive, something invisible. That something, we now believe, is a vast halo of dark matter, surrounding each galaxy like a ghostly sphere, reaching far beyond the visible edge. This halo doesn't emit light, but it holds the galaxy together, like an unseen hand cupping a spiral of stars. Vera Rubin, whose work we'll explore more deeply next, played a key role in documenting these curves. Through years of precise observation, she and her colleagues confirmed that this phenomenon was not rare, it was the rule. The galaxies weren't broken, the theories weren't flawed. Instead, there was something more, something no one could see, but everyone could now measure through motion. There's something deeply poetic about this. The stars are not drifting, they are obeying a law that includes more than meets the eye. Gravity is still in charge, but gravity is responding to a mass that hides from light. Let that settle for a moment. Every time you look at an image of a galaxy, glowing and serene, remember that what you see is only the center of the story. The outer structure, the force holding it all in place, is invisible. It doesn't twinkle, it doesn't shine, but it shapes the very fabric of the spiral. Dark matter doesn't disrupt the laws of physics, it completes them. Not all revolutions come with thunder. Some arrive quietly, carried by patience, precision, and a long gaze through a telescope. Such was the legacy of Vera Rubin, a scientist who didn't shout her discoveries, but let the stars speak for her. In the 1970 seconds, Rubin and her collaborator Kent Ford began a careful, systematic study of spiral galaxies. While others had touched the mystery of flat rotation curves, Rubin dedicated herself to it fully. She wasn't chasing headlines. She was measuring motion, one galaxy at a time. What she found would forever reshape astronomy. Galaxy after galaxy showed the same result. The stars at the outer edges were spinning just as fast as those near the center. This wasn't a fluke. It wasn't a strange exception. It was a pattern, a law. Rubin's genius was not in discovering something brand new, but in refusing to dismiss what didn't make sense. She trusted the data. She trusted the sky. At a time when dark matter was still an uncertain, uncomfortable idea, her observations made it unavoidable. You couldn't explain galaxy dynamics without it. The math no longer worked without this invisible mass. And Vera Rubin made that realization impossible to ignore. She didn't do it through grand proclamations. She did it through graphs, dozens of them, each one a quiet whisper that said, "This galaxy is not what it seems." Imagine that work. Not one breakthrough, but 100 small confirmations. She didn't look for the unusual. She looked for what was consistent, what was stable, what kept repeating. In doing so, she brought clarity to chaos. Rubin's rotation curves confirmed that spiral galaxies are embedded in vast halos of unseen matter. The visible stars make up only the glowing center. The dark matter extends far beyond, shaping the orbits of stars, the balance of the galaxy, and the structure of the cosmos. It wasn't flashy, it wasn't dramatic, but it was solid, beautiful science, and it changed everything. Rubin's work helped shift dark matter from a fringe idea to a mainstream pillar of cosmology. Today, no serious model of galaxy formation or cosmic structure ignores it. What was once theoretical is now foundational. And yet, Rubin herself remained grounded, kind, thoughtful. She was one of the few women in a field dominated by men, and she didn't just endure, she excelled. Not only for what she discovered, but for how she did it, with elegance, humility, and quiet strength. She once said, "There is no problem in science that can be solved by a man that cannot be solved by a woman." And the universe, it seems, agreed. Her legacy is not just data points and published papers. It's the way she looked at the universe, with respect for its mystery and with trust in its patterns. She knew the cosmos would reveal its secrets, not all at once, but slowly, like a spiral unwinding in the dark. Today, when we speak of dark matter, we walk paths she mapped for us. We trace curves she measured. We ask questions she gave us permission to ask. Let that rest in your mind like starlight, soft, steady, and far-reaching. The night sky still looks the same to the eye. But thanks to Rubin, we now know there's more to it than we see. Beneath every galaxy lies a shadow of mass we cannot touch, but cannot ignore. And it was a woman, steady and undeterred, who pointed and said, "Look again." When we imagine the universe, we often picture it as scattered, a collection of stars, galaxies, and dust floating through infinite darkness. But in truth, the cosmos has structure. Beneath the apparent chaos there is a pattern, a vast and delicate architecture we cannot see with our eyes, but which dark matter reveals with quiet certainty. It's called the cosmic web. Stretching across billions of light years, this web is not woven from light, but from gravity. It connects galaxies, clusters, and superclusters in filaments, thread-like structures made of dark matter. Between these filaments lie vast voids, immense spaces where very little matter resides. It's not an even spread, but a pattern, like veins through a leaf or cracks in dry earth. Astronomers discovered this structure not by looking through telescopes alone, but by combining maps of galaxies with the results of powerful computer simulations. When they included only visible matter, the universe in their models looked wrong, too smooth, too scattered. But when they added dark matter, something remarkable happened. The structure snapped into place. Galaxies formed along filaments, clusters gathered at intersections, voids opened between them. The simulation became a mirror. The real universe, it turns out, is not a loose scattering. It is held together by an unseen design, and that design is drawn by dark matter. Imagine a spider web stretched across a forest path, invisible until the morning dew settles across its threads. Suddenly, what was hidden becomes visible, not because the web changed, but because something revealed it. That's what dark matter does. It holds the shape of the cosmos, and once we knew how to look for it, we saw it everywhere. The cosmic web is not something we can photograph directly, but we can infer its existence by how galaxies move, where they cluster, how light bends, and how the universe expands. It is the skeleton of the cosmos, a framework built not of light, but of shadow. Each filament of this web is a current of dark matter. Along these filaments, galaxies are born and pulled into place. Where filaments intersect, clusters of galaxies form, dense cities in the sky, lit by stars but governed by something unseen. Even our own Milky Way is part of this web. We are not isolated. We are anchored by invisible strands that reach out across unimaginable distances. We are part of a larger fabric, one that binds galaxies like islands connected beneath the sea. This structure explains why galaxies aren't randomly scattered, why the universe has walls and rivers and empty basins. Dark matter's gravity guides the flow of matter like hidden banks shaping a river's course. The visible universe floats along these currents, unaware of the invisible tides beneath it. Let that settle. What looks like emptiness is actually design. What seems like disorder is part of a deeper symmetry. The cosmic web challenges our sense of scale. We are used to thinking in terms of planets, maybe stars, but these filaments stretch across hundreds of millions of light years. They don't belong to one galaxy, they define the placement of thousands. Yet, they remain invisible, detectable only through motion, light distortion, and simulation. And at the heart of it all, dark matter, silent, cold, unlit, but utterly essential. It's a kind of beauty that reveals itself slowly. The more we listen to the motion of galaxies, the more we begin to see the shape of what we cannot see. A whisper becomes a line. A curve becomes a map. The universe becomes not just vast, but connected. We are not drifting randomly through space. We are cradled in a structure more ancient and expansive than we can imagine. a structure drawn not in stars, but in gravity, a web of darkness, quietly holding the light. Sometimes, we learn the most about something not by looking at it directly, but by watching how it changes the things around it. This is the story of gravitational lensing, a quiet bending of light that tells us where the invisible hides. Einstein predicted it. If gravity could bend space, then light, which travels through space, should bend too. That means a massive object, like a galaxy or a cluster, could act like a lens, distorting the light that passes near it. It took decades to observe, but when we finally saw it, the effect was unmistakable. Light from distant galaxies was curving, stretching, or doubling around things that couldn't be fully seen. A galaxy behind another galaxy might appear smeared into an arc. A distant cluster might form a ring of light, called an Einstein ring, around a central mass. But the most intriguing cases are those where the light bends around nothing visible at all. Gravitational lensing allows astronomers to map mass, not just light. And time after time, these maps show something startling. Most of the mass isn't where the stars are. It's in the dark spaces. The light is bending around invisible halos. This technique gave scientists one of their strongest tools for studying dark matter. Because dark matter doesn't emit or absorb light, it doesn't show up in photos, but it has mass, and mass bends light. So while we can't see dark matter directly, we can see the warping it causes. Imagine holding a clear marble in front of a distant streetlight. The marble bends the light, not because of its color, but because of its shape and mass. Now imagine doing that with space itself. That's gravitational lensing. And in many places, the marble is missing, but the bending still occurs. That's dark matter at work. One of the most striking examples of this is the Bullet Cluster, a pair of galaxy clusters that collided millions of years ago. The visible matter, the stars and hot gas, interacted and slowed down. But gravitational lensing showed that most of the mass had moved on ahead, unaffected. The stars and gas glowed in one place, but the gravity, the true mass, was centered elsewhere. It was as if the shadows had walked ahead of the light. Gravitational lensing doesn't just confirm that dark matter exists, it shows us where it is. It lets scientists draw maps of invisible structures, revealing webs and halos and currents we can't see any other way. The effect comes in two forms: strong lensing, which creates dramatic arcs and rings, and weak lensing, which subtly stretches the shapes of galaxies across the sky. The latter is harder to detect, but when applied across thousands or millions of galaxies, it reveals enormous patterns, dark structures sprawling across the cosmos, tugging at light from behind the curtain. There's something deeply beautiful about this. The idea that light, which moves so fast and so far, can still be bent by something silent. That the universe leaves fingerprints not in brightness, but in distortion. That even when the source is invisible, its presence remains undeniable in the way space warps and curves. Gravitational lensing is more than a trick of light. It's a message from gravity itself. Something is here. Something is strong. Something cannot be seen but cannot be denied. In a way, it's like listening to echoes in a canyon you cannot enter. You shout into the dark, and what returns tells you something about the space you cannot see. Dark matter continues to evade direct detection, but in the bending of light, it speaks. And in that silent distortion, the universe tells a different kind of story, one shaped not by what shines, but by what shifts. In most of the universe, things happen slowly. Stars take millions of years to form, galaxies drift for billions, but sometimes the cosmos surprises us with motion that is sudden and violent. The Bullet Cluster is one such place. Roughly 3.8 billion light-years away, two enormous clusters of galaxies collided. Imagine it. Hundreds of galaxies, each containing billions of stars, moving toward one another across the void, until finally they pass through each other in a titanic, silent crash. Not a crash like cars, but a passing through, like two clouds colliding in the sky. Clusters are not made mostly of stars, they're made mostly of hot gas, a searing fog that glows in X-rays and carries most of the cluster's visible mass. When the two clusters collided, their gases slammed together, slowed down, and heated up, forming a dense, glowing core in the center. But the galaxies themselves? They barely noticed. Separated by so much empty space, most of the stars passed by without a single collision. Like snowflakes drifting through fog, they continued on. And yet, something strange remained. When astronomers studied the bullet cluster, they looked at two things: the X-ray glow from the gas and the gravitational lensing, how the cluster bent light from even more distant galaxies behind it. What they saw didn't match. The hot gas, the part we could see, was mostly in the center, where the collision occurred. But the mass, as revealed by gravitational lensing, was somewhere else. It had moved ahead of the gas, continuing on either side of the collision. In other words, the gravity had separated from the light. This was one of the clearest, most dramatic pieces of evidence for dark matter ever observed. If visible matter alone were responsible for the cluster's gravity, then the center, full of glowing gas, should have bent the light the most. But it didn't. The strongest gravitational pull came from two areas flanking the collision site, precisely where the galaxies had passed through, places where there wasn't enough visible matter to explain the lensing. The only explanation was invisible mass, dark matter, that had passed through the collision undisturbed, just like the galaxies. Think of it like this. You toss two handfuls of feathers at each other. The feathers are slowed by air resistance, forming a tangle in the center. But imagine invisible cannonballs mixed into the feathers. The cannonballs don't stop. They pass straight through, unaffected, continuing on their path. You don't see the cannonballs, but you see their effect. You see the table bend where they land. That's gravitational lensing. The bullet cluster is not just beautiful, it's brutal. A direct glimpse at two massive systems colliding, their visible parts slowed by pressure and heat, their invisible parts pushing on. It's one of the best astrophysical arguments against alternatives to dark matter, like modified Newtonian dynamics. In MOND, gravity itself is altered to explain what we see. But in the bullet cluster, the mass and the matter separate, and only a second invisible component, dark matter, can explain the outcome. This cluster doesn't just support the existence of dark matter, it paints it in motion. It shows us that dark matter behaves differently than ordinary matter. It doesn't collide, it doesn't heat up, it doesn't radiate, it simply moves through, ghost-like, but real. And through the lensing of distant light, we can track its silent path. The bullet cluster reminds us that even in cosmic violence, truth emerges. When things are torn apart, we see what holds them together. Let that image rest with you for a moment. Two clusters crashing through each other like silent giants, their light thrown into chaos, but their gravity walking ahead, calm, steady, invisible. Dark matter does not glow, but in places like this, it becomes impossible to ignore. The visible parts of the universe are just the surface of something deeper. Behind every star, behind every galaxy, there is something else, something silent, something unseen, shaping their motion without ever revealing its own. Astronomers once believed that the light of the cosmos told the whole story, that by counting stars and mapping glowing clouds of gas, they could understand the structure of the universe. But again and again, the observations told a different tale. In many galaxies, the brightest regions do not always correspond to the regions with the strongest gravitational pull. Telescopes detect glowing arms of stars, shining clusters, radiating clouds, but the invisible hand guiding them lies elsewhere. The stars move as if tethered to something larger, something more massive than the light suggests. It's as if a great unseen sculpture lies beneath every galaxy, and the stars trace its outline without ever touching its core. They spin not only because of the mass we can see, but because of a deeper gravity, one shaped by matter we cannot detect directly. This is the heart of dark matter's role in the universe. Not to shine, not to collide, not to be touched, but to hold everything together. It moves quietly, it exerts force without resistance. It shapes the grand design of space. When astronomers map these hidden influences, they often find that the mass of a galaxy, its true gravitational center, lies not in the brightest regions, but in darker places, sometimes on the edges, sometimes in areas that appear almost empty. And yet, The pull is there, measurable, predictable, real. This disconnect between light and gravity has become one of the defining mysteries of modern astrophysics. If gravity were caused only by visible matter, these motions would be impossible. The galaxies would not hold together, the stars would not stay in orbit, the structures of the universe would drift apart, but they don't. They remain, held in form by something we cannot see. Dark matter reveals itself not by appearance, but by consistency, in the way stars rotate, in the way galaxies stay bound, in the quiet gravitational logic that guides motion across billions of light years. And what's most remarkable is that this invisible matter does not resist. It does not emit or absorb radiation. It doesn't interact with light at all. It simply moves forward, as if indifferent to the visible world, yet indispensable to its shape. Even now, scientists search for what dark matter might be. A particle? A field? A new kind of structure? We don't yet know. But we know it's there, because without it, the universe would look very different. There's something strangely comforting in this. The idea that not everything needs to be visible to be real. That something can be absolutely essential, yet make no sound, no flash, no demand to be seen. The stars rely on it. The galaxies are shaped by it. The universe is drawn along its silent lines. And in this quiet moment, perhaps that idea can hold you too. As your breath slows and your body softens, you don't need to notice the exact moment rest begins. Sleep doesn't have to announce itself. It can come like gravity, gentle, steady, unspoken. It arrives not to explain, but to hold. You don't have to see what carries you to be carried by it. Most of what we interact with in daily life, air, water, stone, stars, is made of what physicists call ordinary matter. These are atoms, protons, neutrons, electrons, the familiar building blocks. Everything we've ever seen, touched, or measured falls into this category. But when astronomers calculated the total mass of the universe, something astonishing emerged. All the ordinary matter, the stars, the planets, the swirling gas, the dust between galaxies, accounts for only a small fraction of what must be there. The rest is something else, something invisible. This realization came not from a single experiment, but from the accumulation of patterns. Galaxies spinning too fast, light bending in ways it shouldn't, matter behaving as if it were held by something unseen. Over and over again, the visible world proved insufficient. Imagine trying to weigh a ship by measuring only what floats above the waterline. The mass you see is real, but it's only part of the story. The bulk lies hidden below, steadying the vessel. In the same way, the visible matter in the cosmos is the part that glows, but the structure, the stability, comes from what lies beneath. This unseen mass is what we call dark matter, and by every measurement so far, there's much more of it than there is of anything we can see. Ordinary matter interacts through several forces. It responds to light, it heats up, it collides, clumps, scatters, radiates. Dark matter does none of this. It passes through without friction. It forms no atoms. It emits no energy. And yet, it exerts gravity. Strong, consistent, unmistakable. This difference isn't just a curiosity. It reshapes our understanding of what the universe even is. The idea that what we see, the stars glittering across the sky, the luminous arms of galaxies, the glowing gas clouds, represents only a thin trace of reality is humbling and compelling. Scientists have tried to account for every kind of visible object that could hide in the dark. Brown dwarfs, dim stars that never ignited, black holes, faint planets, cold gas, but none of it adds up. Even in combination, these forms of ordinary matter fall short. There's simply not enough of them, and their gravitational signatures don't match what we observe. The evidence has pushed physics towards something more exotic, not dim matter, but different matter, a substance that obeys gravity but ignores nearly everything else. This is where ordinary matter meets its limit. It can't account for the shapes of galaxies. It can't explain why large-scale structures form the way they do. And it can't replace what we now see only through its effects. What's remarkable is how clearly this limitation shows up in the data. Scientists simulate the universe using different ingredients. When they try to recreate galaxy formation using only ordinary matter, the results fall apart. Galaxies don't form. The cosmic web never develops. But when dark matter is included, the model matches what we see in the night sky. In this way, dark matter doesn't replace ordinary matter. It completes it. It holds the scaffolding while ordinary matter paints the surface. It shapes the riverbed while visible matter becomes the water. It defines the structure, then lets everything else move freely within it. This isn't a flaw in our understanding. It's a refinement, a necessary update to a map that now stretches further than ever before. The truth is simple and profound. Most of what exists is not like us. It does not burn, sparkle, or reflect. It does not resist, but it shapes the stars, guides the galaxies, and outlines the vast silence of space. And perhaps it reminds us that just because something is small does not make it central. Just because something is visible does not make it fundamental. What we call ordinary is, in fact, the exception. The cosmos is built on a different foundation, one we can't see, but one that carries everything we do. Sometimes, the clearest path forward begins with eliminating what something cannot be. In the case of dark matter, decades of investigation have been spent crossing out possibilities. The shape of the mystery has grown clearer, not because we've seen the answer, but because we've carefully ruled out everything else. Dark matter isn't just hidden matter. It's fundamentally different from the matter we know. If it were simply composed of familiar particles in unfamiliar places, things too dim to detect or too cold to radiate, we would have found it by now. We've looked, we've listened, and nothing has answered. Many early theories suggested that perhaps the missing mass was made of things like faint stars, drifting planets, or clouds of cold gas, objects that emit little to no light. These would be hard to detect but still made of ordinary matter. Collectively, they were known as MACOs, massive compact halo objects. Astronomers searched for them by watching for subtle flickers in starlight, hoping to catch these dim objects as they passed in front of stars and bent their light. The technique, called microlensing, offered promise, and some objects were found, but not nearly enough. Not enough to explain the movements of galaxies, the warping of light, the stability of clusters, or the shape of the universe itself. Brown dwarfs, sometimes called failed stars, were also considered. So were rogue planets, drifting unbound in the void between solar systems. Massive black holes, too, were proposed as candidates. But all of these are still made of the same kind of matter as we are. They interact with light, with heat, with pressure. They collide, they decay, and most importantly, they don't exist in large enough numbers to account for the gravitational effects we measure. Dark matter, as it behaves, does not clump the way ordinary matter does. It doesn't form disks or clouds. It spreads in halos around galaxies, creating smooth, extended gravitational wells. That's not how gas or stars behave. That's not how planets or dust arrange themselves. The profile is different. The shape is different. And so the substance must be different too. If dark matter were made of ordinary atoms, we would expect it to absorb or scatter radiation. It would leave fingerprints on the early universe, on the light left over from the formation of the first atoms. But we don't see those marks. The cosmic background radiation is too clean, too smooth, too quiet. So we eliminate. One by one, we cross off the familiar options. We strip away every form of visible matter, every arrangement of known particles, every interaction we understand. And what remains is something silent, massive, and unlike anything we've ever touched. Dark matter is not dust in disguise. It is not a veil pulled over the universe. It is something else entirely. Something outside the standard model of particle physics. A new kind of presence. And that absence of identification becomes its own kind of evidence. Because the universe behaves as though something is there. The galaxies spin as if pulled, the light bends as if shaped, the stars orbit as if cradled, and no known substance can explain it. This process of ruling out requires patience, precision, discipline. It means admitting over and over again what something is not, without yet knowing what it is. But in science, as in life, This narrowing can be just as powerful as discovery. It is a sculptor's approach. Subtraction until form appears. We don't yet know what dark matter is, but we know what it isn't. And sometimes, that's how the truth begins. Once scientists accepted that dark matter was not ordinary matter, the search turned toward something more speculative, new particles that might exist beyond the framework of known physics. If dark matter isn't what we already understand, then perhaps it is something entirely new. This idea gave rise to candidates with names as strange as the mystery they aim to solve: WIMPs and axions. WIMPs, or weakly interacting massive particles, are among the most studied possibilities. These particles would be heavy, meaning they have significant mass, but would interact with other matter only through gravity and perhaps the weak nuclear force. That makes them nearly impossible to detect. They would pass through ordinary matter like wind through a forest, without scattering, without slowing, without leaving a mark. For years, scientists hoped that WIMPs might be produced in high-energy particle collisions, like those at the Large Hadron Collider, or that they might occasionally bump into the atoms inside sensitive detectors buried deep underground, shielded from interference. These experiments have become increasingly sophisticated, capable of sensing the tiniest flashes of light or vibrations caused by a single atomic recoil. But the silence has been persistent. Not a single confirmed WIMP detection, not one conclusive collision. As detectors grow quieter and more precise, the absence becomes more eloquent. If WIMPs exist, they are more elusive than we thought. Or they are different from what we imagined. This has led scientists to look in other directions. Enter axions, particles that were first proposed for an entirely different reason: to explain a peculiarity in the behavior of the strong nuclear force. Axions would be extremely light, nearly massless, but present in such enormous quantities that their collective gravitational influence could account for dark matter. Unlike WIMPs, axions would not behave like particles in the traditional sense. They would behave more like a field, spread smoothly across space, rippling faintly like a mist. They would be everywhere, forming a quiet ocean through which stars and galaxies drift. The search for axions is different. It involves looking for strange effects on electromagnetic fields, or trying to convert axions into photons under carefully controlled conditions. These experiments are delicate, slow, and incredibly precise, like trying to catch a whisper in a hurricane. So far, axions have been just as elusive as WIMPs, but the idea remains compelling: that dark matter might not be clumps of particles, but a continuous field, stretching invisibly across space, shaping gravity like an unseen tide. There are other candidates too: sterile neutrinos, supersymmetric particles, even entirely unknown forces. The list is long, the tests are ongoing, and each experiment, even when it yields nothing, helps shape the boundary of what dark matter could be. This process can feel frustrating. The particles refuse to appear, the signals remain silent, but in that silence is progress. Every failed detection sharpens the map. Every unanswered question narrows the field. The mystery is not growing, it's becoming more defined. And the truth is, we've faced this kind of mystery before. Neutrinos, now an accepted part of physics, were once invisible to detection. They passed through the Earth as if it were smoke. For decades, they were hypothetical, used to balance equations, but never seen. It took time, new technology, and new ways of thinking before they emerged from theory into evidence. Dark matter may be on the same path. Somewhere, deep in the structure of the universe, the answer exists. Whether it's a heavy particle like a WIMP, or a ghostly wave like an axion, or something entirely unexpected, we are getting closer. Not by seeing it directly, but by learning what not to expect, and by building better instruments to listen for what remains. The universe is quiet, but it is not indifferent. It holds its secrets not out of cruelty, but out of scale. And piece by piece, silence by silence, the outline becomes clear. To find something that doesn't want to be seen, you must go where nothing else can interfere. That's why the search for dark matter has gone underground, far beneath the surface of the Earth, where silence is more than a sound. It's a condition. In abandoned mines, inside mountain caverns, and beneath thick layers of rock, scientists have built some of the quietest places on the planet. Not quiet in terms of noise, but in terms of interference. These spaces are shielded from cosmic rays, solar particles, and even the natural radiation that seeps from soil and air. They are as close to stillness as we can create, and in that stillness, they wait. Dark matter is expected to be all around us, passing through us at every moment. If it's made of particles, WIMPs, or some other kind, then perhaps, very rarely, one of them will collide with an atom. Not with a crash, not with sparks, but with a tiny whisper of energy. A recoil, a flicker, something measurable, if the detector is sensitive enough, and if all other sources of noise are stripped away. These detectors are elegant in their simplicity, but extraordinary in their sensitivity. Many are tanks of ultra-pure liquid xenon, monitored for faint flashes of light or slight changes in charge. Others use cryogenically frozen crystals, tuned to vibrate at the smallest touch. Some rely on bubble chambers, where a single dark matter interaction could cause a visible trail in a superheated liquid. Each design has the same goal: to capture the moment when something unknown leaves its mark on something familiar. And yet, after decades of searching, these detectors have recorded no confirmed interactions. The silence remains. It is easy to think of that as failure, but in truth, it is a kind of progress. With every experiment that rules out a possibility, the search becomes more focused. We now know where dark matter is not. We know how strongly it doesn't interact, and that narrows the space where it still might be. The underground laboratories are not places of disappointment, they are temples of patience. The scientists who work there are not disheartened by silence. They listen to it, they refine their tools, they try again. In this work, waiting becomes a method. Imagine a room so still that the smallest disturbance, one single atom bouncing back after a collision, could be detected and measured. Imagine engineers and physicists spending years designing machines so precise that they must be assembled in sterile suits, free of dust and vibration, kept colder than space. Now imagine dedicating all that to the chance of seeing something that might not reveal itself at all. That is the nature of this search, not one of flashes and noise, but of shadow and suggestion. It is a kind of science that requires faith, not in belief, but in process, in the idea that knowledge advances not only through discovery, but through the discipline of staying open, staying curious, and asking questions even when the answers are slow to arrive. And the deeper truth is this: just because something hasn't shown itself doesn't mean it isn't there. It may be rarer than we thought. It may interact more weakly, or it may wait for a new kind of detector, a new idea, a better question. The laboratories continue to grow. The detectors become larger, colder, purer. New generations of instruments are being built even now, in deeper chambers, with better shielding. The hope remains, not because the evidence has arrived, but because the universe continues to suggest it must. Somewhere, in the quiet, something is moving, and one day, perhaps, it will leave a mark. The detectors were ready. The calculations were sound. The theories pointed to a realm just beyond reach, something massive, cold, and quiet moving through the cosmos. And so scientists built their instruments, buried them deep, and waited. But the signal never came. No flash of light, no echo, no subtle vibration to say, "Here it is." Instead, there was silence. For many experiments, that silence has lasted years, sometimes decades. But silence in science is not the same as failure. It is data, it is shape. It tells you what something is not, and therefore helps you understand what it might be. The search for dark matter is a rare kind of investigation, one that tests the patience of both machines and minds. Every null result, every stretch of time in which nothing happens, becomes part of the larger picture. Each quiet measurement refines the boundaries of possibility. This is how the scientific process works when the thing you seek is silent by nature. You build better tools. You dig deeper into the earth. You refine your methods until all the background noise is stripped away and only the unknown remains. Some of the most sensitive detectors ever built now wait underground for a single interaction that might never happen in a human lifetime. A lone collision between a dark matter particle and an atom, a flicker of something unknown brushing against the known. And yet, the absence of detection speaks. The theories once predicted that dark matter would interact with ordinary matter more frequently, perhaps once every few days, or once a year in a given detector, but those predictions were wrong. As the detectors have grown quieter and more sensitive, the silence has grown louder. That silence has become a constraint, a boundary. It tells us that dark matter must be even more elusive than expected. If it exists, it must interact more weakly, or possess properties we haven't yet imagined. In this way, silence has become a sculptor. It carves away the theories that do not hold. It shapes what remains into something new. There is a certain beauty in that, a discipline that doesn't depend on results, but on the persistence of the question, the courage to keep listening, even when the response is nothing at all. Imagine sitting in a vast cave, listening for a sound that no ear can hear. You don't know when it will come, or if it ever will, but you keep still. You keep your attention sharp, because in that stillness, something might shift. That is what dark matter research has become, a kind of listening, a kind of discipline, a kind of belief in the value of the unknown. This isn't romanticizing failure. It's recognizing that science is not only about answers, it's about the strength to continue in the face of ambiguity, to accept that the universe does not always reward us with clarity. Sometimes it offers a mystery wrapped in silence and waits to see what we'll do with it. The silence surrounding dark matter has not stopped the search, it has refined it. Theories have evolved, detectors have grown, new candidates, like axions and sterile neutrinos, have risen. Old assumptions have been set aside. The field has grown not in what it has caught, but in what it has ruled out. And still, scientists listen, in the deepest chambers of the earth, in instruments built to hear the unheard. The waiting continues, not out of desperation, but out of dedication, because even in silence, the universe is speaking, and the shape of what it says becomes clearer every day. There is a kind of silence that only space can offer, not the absence of sound, but the absence of interruption. No wind, no waves, no voices, just the quiet press of gravity holding everything in its place. If you look at a spiral galaxy, you might notice how its stars cling to their paths far longer than they should. The outer edges move faster than expected, held by something that isn't visible, not a glow, not a force you can point to, but a presence. That presence is dark matter, and its reach is vast. Astronomers call it a gravitational halo, a sphere of invisible mass that wraps around galaxies like a shell. It doesn't collapse into stars, it doesn't form planets. It simply surrounds, steady and wide, dictating the pace of motion. Without it, galaxies would drift apart, the stars would fly free. But they don't. They hold together, quietly obeying a law they cannot see. There is something poetic in that. The idea that what is unseen can still be the anchor, that what exerts no light can still define the path. You don't have to see a current to feel its pull. Dark matter doesn't flare or scatter or collide. It moves through space with patience. It allows the bright things to shine while it holds the frame behind them. Imagine being inside that kind of stillness. No pressure to glow, no need to be noticed, just the quiet confidence of holding everything together. This invisible structure is everywhere, not just in galaxies, but between them, threading through the universe in long, delicate strands. It forms a vast cosmic web, guiding the distribution of matter on the largest scales. Where the strands intersect, galaxies form. Where they stretch out, voids appear. And still, we've never seen it directly. We map its shape by watching how galaxies move, how light bends, how space behaves under its weight. It is always detected through effects, never through presence, like tracing wind by watching the grass. Even now, dark matter remains one of the most measured but least understood parts of the cosmos. We have mapped its reach, we have modeled its behavior, but we have not touched it, or caught it, or seen it glow. Perhaps that's why it feels so compelling. It reminds us that knowing does not always require seeing. That certainty can arrive through patterns, not proof. Like so many things we trust without evidence, love, memory, instinct, dark matter is real in the way it shapes reality, not in the way it announces itself. And now, as you settle into this quiet moment, perhaps your own thoughts begin to stretch. Not sharply, not brightly, but gently, as if held in place by something calm and unseen. If sleep begins to drift toward you, let it. There's no urgency, no command, just gravity doing what it has always done, holding things close, letting others pass, shaping paths without ever being seen. To understand what dark matter is, it helps to understand what it has done. Not recently, but long ago, at the very beginning of time, when the universe was still hot, dense, and unimaginably young. In those first moments, everything was in motion. Matter and energy exchanged forms freely. Particles collided, fused, decayed, and scattered. The universe was a roiling soup, glowing and thick. But even then, the seeds of structure were being sown, not evenly, not perfectly. There were tiny variations, slight differences in temperature and density across different patches of space. These wrinkles, too small to notice at first, became the blueprint for everything that followed. And this is where dark matter may have played one of its most crucial roles. Ordinary matter, the kind that forms stars and planets, interacts with light. That means it also feels pressure from light. In the early universe, this pressure prevented it from clumping together. Every time gravity tried to pull gas into denser regions, radiation pushed it back out. It was a tug of war, and for a long time, the light was winning. But dark matter does not interact with light. It is immune to radiation. It could start clumping immediately, even when everything else was still too hot and chaotic to settle down. While visible matter was still bouncing in the glare of the young cosmos, dark matter was already beginning to gather in quiet pockets, dense halos forming invisibly in the dark. These halos became the scaffolding of the universe. Later, when the universe cooled enough for atoms to form and light to travel freely, visible matter began to fall into the wells that dark matter had already carved out. The galaxies we now see were born in the gravitational hollows that dark matter had prepared. Without that invisible scaffolding, there may not have been enough time for galaxies to form. The universe would have remained smooth and structureless, expanding, glowing, but empty of stars, planets, or life. This understanding comes not from imagination, but from measurement. We can see the imprint of those early variations in the cosmic microwave background, the faint afterglow of the Big Bang. This light, still traveling across the universe today, carries tiny fluctuations in temperature and density, and those fluctuations match what we would expect if dark matter had been present, shaping the landscape from the very start. Simulations show it clearly. Without dark matter, the early universe stays too smooth. With dark matter, structure emerges, galaxies form, clusters appear, a universe like ours becomes possible. In this sense, dark matter isn't just something that explains what we can't see. It's something that allowed everything we do see to exist. Its role was quiet, but foundational. As the universe aged, dark matter continued to shape it. Where dark matter was dense, galaxies bloomed. Where it was sparse, voids stretched out. It did not shine, it did not ignite, but it organized the light around it. This is one of the strange ironies of the cosmos. The things we cannot see are often the things that gave shape to everything we can. And yet, dark matter has left no trace of itself beyond gravity, no particles found, no interactions observed. Only the patterns it helped sculpt remain, like footprints on frozen ground, long after the walker has passed. To study dark matter is to study echoes, effects, consequences. But that is often how science works. We learn not just by what we touch, but by what leaves an impression. The early universe, still glowing in the oldest light, tells us that dark matter was there from the beginning. Quiet, steady, invisible. And through its silent influence, the universe took on its shape. A shape that includes everything. Stars, galaxies, us. If you could pull back far enough, far beyond Earth, beyond our galaxy, beyond even the clusters of galaxies, you would begin to see a shape emerge. Not a random scatter of stars, but a vast and delicate pattern that stretches across the universe like lace. This is the cosmic web, the largest structure ever discovered, and it was shaped by something we cannot see. Galaxies do not float through space independently. They gather in clusters, linked by filaments of dark matter and gas that extend for hundreds of millions of light years. Between these filaments lie voids, immense regions of almost nothing, where matter is sparse and galaxies are rare. These filaments and voids form the architecture of the cosmos, and dark matter is the invisible hand that spun the threads. When the universe was still young, dark matter began to clump under its own gravity, pulling together in long strands. These strands pulled visible matter along with them, providing the scaffolding upon which galaxies could form. Over billions of years, gravity reinforced the structure, deepening the voids and thickening the filaments. Today, we can simulate this web with extraordinary precision. We feed the physics we know into vast computer models: gravity, fluid dynamics, the effects of dark matter. What emerges looks astonishingly like what we observe in the real universe. When we compare those simulations to actual sky surveys, maps of galaxies and clusters collected by telescopes, the resemblance is uncanny. The reason this structure is so compelling is because it should not exist without dark matter. Ordinary matter alone does not have the mass or the time to create such vast and intricate forms. Something more massive, more ancient, and more stable had to come first. That something is dark matter. The cosmic web is not just beautiful, it is functional. Galaxies move along these filaments like beads on strings, drifting toward intersections where clusters form. These intersections, called nodes, are regions of intense gravitational pull, where thousands of galaxies may gather and collide over time. Even our own Milky Way is part of this web. It belongs to a small group of galaxies known as the local group, which is itself drifting toward a larger structure called the Virgo cluster. That cluster is part of the Laniakea supercluster, a massive continent of galaxies flowing through one of the web's filaments. All of this movement is governed not by visible structures, but by the pull of dark matter. There is no central command, no blueprint, just gravity, working patiently across time and space, drawing lines that matter follows. We do not see the web directly, but we infer its shape through the motions of galaxies, the distribution of clusters, and the gravitational lensing of light that passes through it. It is as if the universe reveals its skeleton only in silhouette, visible through the way it bends and guides the things we can detect. Dark matter is the weaver of this structure, not through intention, but through gravity alone. And even now, the web is evolving. Filaments continue to pull matter inward, galaxies collide and merge, clusters grow, the web tightens in places and stretches in others. It is not static, but alive with the slow pulse of cosmic motion. To see the universe at this scale is to realize how much of it remains invisible, not just in terms of darkness, but in terms of understanding. The threads that bind galaxies together do not announce themselves, they do not glow, but they shape the universe all the same. Dark matter does not fill the void, it defines the shape around it. Light travels in straight lines, unless gravity tells it otherwise. This strange truth, predicted by Einstein and confirmed a century ago, has become one of the most powerful tools for revealing what we cannot see. When light from a distant object passes near a massive body, like a galaxy or a cluster, the path it takes bends. Not because the light itself is being pushed or pulled, but because space itself is curved by mass. Light simply follows the curve. This effect is called gravitational lensing, and it is one of the clearest signs that dark matter is real. Sometimes, the lensing is dramatic. A single galaxy, sitting between Earth and a more distant one, can act like a lens, stretching and magnifying the background light into rings, arcs, or distorted copies. These are not tricks of the eye. They are measurements. By studying the way light is bent, scientists can calculate how much mass is present in the lensing object, even if that mass is invisible. And what they find, again and again, is that there is more gravity than there is visible matter. A galaxy might contain 100 billion stars, but its gravitational lens reveals 5 or 10 times more mass than the stars and gas account for. The extra mass is invisible, untouchable, and dark. That difference is not small. It is consistent across galaxies, clusters, and even the large-scale structure of the universe. Wherever we measure gravity by how light bends, we find too much gravity to be explained by what glows. Sometimes, gravitational lensing is subtle. Weak lensing, as it's called, involves tiny distortions in the shapes of thousands or even millions of background galaxies. The effect is so small that it only becomes clear when the data is averaged over huge fields of view. But even then, the fingerprints of dark matter appear, consistent, persistent, unavoidable. These patterns show us how dark matter is distributed across space, not as points but as smears, halos, and filaments. The data forms maps, gravitational topographies of the invisible. From them, we can reconstruct the shapes of things we cannot see. In this way, lensing has become a kind of indirect vision, a way to see mass without light, and that makes it invaluable in the study of dark matter. Some of the strongest confirmations of dark matter's existence have come from gravitational lensing. One of the most famous examples is the Bullet cluster, a collision of two galaxy clusters. As the visible matter collided and slowed, the dark matter, detected through its gravitational lensing effect, passed through unimpeded. The separation between the visible and the gravitational mass is stark. If modified gravity were the explanation, the mass would stay with the visible matter, but it doesn't. It separates. The Bullet cluster, like so many lensing observations, tells a story that can't be denied. The mass that bends light is not the same as the mass that shines. This distinction is profound. It means that gravity sees something we don't. That light, though fast and free, is still guided by hands we cannot trace. And those hands are made of dark matter. The tools to measure this are improving. Telescopes like Hubble, Euclid, and the Vera Rubin Observatory are giving us increasingly detailed maps of gravitational lensing. With each new observation, the universe's invisible scaffolding becomes clearer. Lensing doesn't just reveal where dark matter is. It shows us how it moves, how it clumps, how it responds to cosmic evolution. It is our most direct look into the dark. When you cannot touch something and cannot see it, but you can measure its influence with precision, you begin to understand it. Slowly, indirectly, but meaningfully. Light still travels across the cosmos as it always has. But now we know to watch not just where it goes, but how it bends. And in that bending, the outline of the invisible becomes unmistakable. Belief in the unseen is not a matter of faith in science, it's a matter of evidence. Dark matter, though invisible, has left a trail so long and so consistent that denying its presence would mean turning away from the map the universe has drawn for us. Over the decades, astronomers have noticed the same strange imbalance in system after system. Galaxies rotating too fast, galaxy clusters held together more tightly than their visible matter could account for, light bending where no luminous object appears. Again and again the same message emerges: the gravity is stronger than the glow. One of the earliest signs came from galaxy rotation curves. If you imagine a galaxy like a giant spinning disk, you'd expect the stars at its outer edges to move more slowly than those near the center, just as the outer planets in our solar system orbit the sun more slowly than the inner ones. That's what Newtonian gravity predicts. But galaxies don't follow that pattern. The stars at their edges orbit just as fast as those near the core, defying expectation. The only way to explain this behavior is to assume there's much more mass in the galaxy than we can see, mass spread out in a wide halo, unseen but gravitationally powerful. Then came the study of galaxy clusters. These massive gatherings of hundreds or thousands of galaxies should, by the laws of physics, fly apart unless something is holding them together. The visible matter alone, stars, gas, dust, is not enough. But once again, the gravitational forces suggest there is more. Something else is keeping the galaxies bound. That something doesn't shine. It doesn't glow in radio or X-ray or visible light, but it makes its presence known through gravity. Gravitational lensing, as explored earlier, added another layer of confirmation. Light from background galaxies bends around clusters in ways that don't match up with the distribution of visible mass. The distortion patterns only make sense if you include large amounts of dark matter. There are other clues too. The way galaxies clump, the way the universe expanded in its early stages, the delicate patterns frozen in the cosmic microwave background. All of them point to a universe where dark matter is not an exception, it's a foundation. But even with all this indirect evidence, the central mystery remains. What is it? Some proposed particles have names: WIMPs, weakly interacting, massive particles, axions, sterile neutrinos. These particles would rarely interact with ordinary matter, which would explain why we haven't detected them directly yet. Detectors buried deep underground, shielded from cosmic radiation, wait for a faint interaction, a flash, a signal, a nudge that would confirm their presence. So far, none have found it, but the search continues. That lack of direct detection does not erase the gravitational map we've built. We have measured the movement of galaxies across billions of light years. We have seen clusters collide, and light bend, and structures form in patterns that ordinary matter alone cannot explain. In science, when enough different methods point to the same conclusion, confidence grows. Each piece of evidence supports the next, like overlapping footprints in a field of snow. Taken alone, each may be uncertain. Together, they form a path. So why do scientists believe in dark matter? Not because they want to, not because they imagine it, but because time and again, nature behaves as though it's there. And when theory and observation diverge, it's the observation that demands our attention. Belief in dark matter is belief in the universe's consistency. It's a willingness to follow the trail of evidence, even when it leads into shadow. It's the understanding that not all reality shines, and that some of its most important parts never will. Far beneath the surface of the Earth, in quiet caverns shielded from radiation and cosmic noise, machines wait in the dark. They are not large or loud. They don't beam signals or sweep the sky. They simply listen, hoping, one day, to catch a whisper from the invisible. These are the dark matter detectors, built not to look outward, but inward, not to chase light, but to feel the faintest tremor that light cannot carry. If dark matter is made of particles, real, physical entities with mass and motion, then perhaps one of those particles will, at some point, collide with ordinary matter, not dramatically, not explosively, but just enough to leave a trace. This is the hope that drives these detectors. Most are buried deep underground, kilometers beneath rock, in abandoned mines or mountain laboratories. The Earth above acts like a shield, blocking cosmic rays and background radiation that might confuse or overwhelm the instruments. In the quiet, detectors become sensitive enough to notice what would otherwise be lost in noise. One type uses large vats of liquid xenon. If a dark matter particle collides with a xenon atom, it might cause a tiny flash of light and release an electron. Detectors immediately record the location and strength of the signal. The instruments are so sensitive that they can detect interactions smaller than what a single photon might trigger. Yet, they wait for years without a definitive result. Other detectors rely on supercooled crystals. If a particle hits an atom in the crystal lattice, the vibration, called a phonon, can be measured. These experiments look for heat that shouldn't be there, for energy that came from something passing through undetected by all other means. In all cases, the goal is the same: isolate the rarest event imaginable, and the challenge is enormous. Because dark matter doesn't seem to interact with electromagnetic force, it doesn't emit or absorb light. If it interacts with regular matter at all, it must do so through gravity or possibly through forces even weaker. That makes detection less like catching a fish and more like waiting for a shadow to touch water. Yet the work continues. The people behind these detectors are meticulous. They calibrate instruments down to the atomic level. They remove every possible source of interference. They repeat results again and again. And still, the noise of the world leaks in. A passing muon, a tiny impurity, the hum of electronics. All must be accounted for, ruled out, and filtered, because a single true signal, if ever found, would change everything. It would mean that dark matter is not just a gravitational ghost, but a tangible thing, something that exists in the same universe of particles as we do, something that could be studied, understood, even classified. To catch that moment, years of stillness are accepted. Patience becomes a scientific tool. Meanwhile, theorists adjust models. Some suggest dark matter is not made of one kind of particle but several. Others argue it may not interact with regular matter at all, and that only gravity can ever betray its presence. Some imagine entire dark sectors, hidden counterparts to every known particle, interacting in a shadow universe that mirrors our own. Whatever the answer, the search is worth it. Even silence can be a clue. If nothing is ever found, it tells us something important, that our ideas must evolve, that dark matter might be even stranger than we imagined, that the universe may still be hiding its deepest structures behind rules we don't yet understand. So the detectors remain in place, watching nothing, listening for the improbable, ready to confirm the presence of something that, until now, has only left footprints in the stars. And if the whisper comes, it will arrive not with certainty, but with mystery. A ripple, a flicker, a tap on the shoulder of the known. What if dark matter isn't just made of stray particles lurking in the spaces between galaxies, but is part of an entire hidden realm, a shadow universe, parallel to our own? It's a question that physicists now take seriously. We already know that dark matter does not interact with light. It doesn't reflect it, absorb it, or emit it. That makes it invisible to traditional detection. But some scientists have proposed that dark matter may be more than just elusive. It may have its own versions of particles, forces, and perhaps even chemistry. Not a mirror of our universe, but a sister, separated by rules we barely understand. This idea is called the dark sector. In this model, dark matter isn't just one particle, it's a whole category of them. Just as our matter is built from protons, neutrons, and electrons, the dark sector could be built from its own ingredients. These components might interact with each other through forces entirely distinct from those in the standard model of physics. There might even be dark photons, dark atoms, or something far stranger. If this sounds like science fiction, it's worth remembering. The known universe already defies everyday logic. Time bends, space expands, particles behave like waves. If nature allows such oddities in the visible world, why would it be any less inventive in the unseen one? Some versions of the dark sector propose that dark matter occasionally interacts with normal matter through a kind of portal, not a doorway in space, but a mathematical connection between forces, an interaction so faint it would take the most sensitive detectors decades to glimpse. These theoretical portals offer a way to test the idea. If even one interaction could be found, it would crack the wall between the visible and the hidden. So far, there is no direct evidence, but the idea solves puzzles. It could explain why dark matter is so stable, why it clumps in halos, and why it avoids collapsing into dense objects like stars. A dark sector might even have its own dark radiation, dark light, and dark forces, each influencing dark matter just as electromagnetism and gravity shape our world. There's even a radical thought. Perhaps the dark sector contains its own versions of complexity, structures, perhaps even its own story of evolution, not visible, not audible, but present. This speculation goes far beyond what we can test today. But science often begins at the edges of the known. The idea of atoms once seemed fanciful. So did quarks, and black holes, and gravitational waves. Discovery has a habit of catching up to imagination. For now, the dark sector remains theory, a way to explore the boundaries of what dark matter might be. It reminds us that even after centuries of exploration, most of the universe is still uncharted, not in space, but in substance. And it leaves us with a humbling thought, that the cosmos may hold not one world, but two, one of light and one of shadow, entangled by gravity, separated by silence. If you find your mind drifting as the idea settles in, that's all right. Sleep sometimes arrives when the boundaries blur, when the world you know starts to stretch into the unknown, and the darkness no longer feels empty, but full of meaning just out of reach. Dark matter explains a great deal, but not everything. For all its elegance, the theory has blind spots, places where predictions don't quite align with observation. These gaps don't disprove dark matter's existence, but they do invite caution. They remind scientists that even well-supported ideas must be tested again and again, especially when the object of study cannot be seen. One of the known issues is called the core cusp problem. According to simulations, if dark matter forms halos around galaxies, those halos should have dense centers, or cusps, where the gravitational force is strongest. But when astronomers measure the rotation curves of small galaxies, especially dwarf galaxies, they find that the matter in the center is more spread out. The dense peak expected by theory is replaced by a gentler slope, a core, not a cusp. This discrepancy suggests that something is missing from the models. Either dark matter behaves differently in small systems, or something else, perhaps feedback from stars or supernovae, reshapes the distribution of matter. The answer isn't clear. Another problem is called the missing satellites problem. Simulations of dark matter suggest that large galaxies like the Milky Way should be surrounded by hundreds or even thousands of smaller satellite galaxies, each formed from its own pocket of dark matter. Yet, when astronomers look around our galaxy, they find far fewer. Only a few dozen satellites have been observed, and while new ones are occasionally discovered, the count still falls short of predictions. Some argue that many satellites may simply be too faint to see. Others think that dark matter may prevent star formation in smaller halos, leaving them invisible in every spectrum. Still, it's a tension between theory and observation. There's also the too big to fail problem. Among the few satellites that have been observed, some appear too massive to be missing in any dark matter simulation. They should form stars and be easy to spot. Yet, they remain oddly quiet or absent altogether. This challenges assumptions about how dark matter interacts with baryonic matter, ordinary atoms. Then come galaxies that seem to defy dark matter altogether. A few galaxies, rare but confirmed, appear to have very little dark matter. They behave as though their gravity can be explained almost entirely by the stars and gas they contain. This isn't necessarily a fatal blow to the dark matter theory. Some models suggest such galaxies could form under special conditions, but it raises eyebrows. If dark matter is essential to galaxy formation, why do some galaxies get by without it? Some physicists suggest an alternative, modified gravity. Instead of assuming invisible matter, perhaps the laws of gravity themselves change on large scales or under certain conditions. These models, often grouped under names like MOND, modified Newtonian dynamics, try to explain the same observations without invoking unseen particles. They have had some success in matching galaxy rotation curves, but fail in other areas, like galaxy cluster dynamics and gravitational lensing. Most cosmologists still favor dark matter, but modified gravity remains part of the discussion. None of these issues prove dark matter is wrong. In fact, most of them exist because the theory has been pushed so far, tested on so many scales, in so many environments, that inconsistencies are inevitable. The more precise our measurements become, the more demanding our theories must be. Science thrives on these tensions. They are not signs of failure, but signs of life. Every inconsistency is a clue. Every mismatch is a doorway. The very act of confronting these problems makes the theory stronger, or leads to something better. Dark matter, as a concept, holds up remarkably well, but where it doesn't, it points toward new physics, new possibilities, and perhaps new kinds of matter entirely. The theory may bend, it may even break, but in that breaking, a deeper understanding of the universe waits to be uncovered. Without dark matter, the universe as we know it would not exist, not in its current shape, not with its galaxies, its clusters, or the intricate web that stretches across billions of light years. The stars would not have gathered, the galaxies would not have formed, the entire cosmic structure would collapse, or never rise at all. Dark matter is not just a mysterious presence in the background, it is the scaffolding upon which visible matter hangs, a framework that guided the early universe like bones give shape to a body. In the first moments after the Big Bang, the universe was a hot, dense soup of particles and radiation. Over time, tiny fluctuations in density began to grow, seeds of future galaxies. But radiation moves fast, and ordinary matter interacts with it, scattering and slowing. These effects would have smoothed out those tiny differences before anything could clump together. Dark matter, however, is different. It does not interact with light, so it was free to begin clumping almost immediately. It gathered into gravitational wells, deepening pits in space, long before atoms could cool and settle. Once those atoms did settle, they followed the dark matter's lead. They fell into its gravity. They formed stars. They built galaxies. Even now, galaxies swirl not around themselves, but around massive dark halos. These halos extend far beyond the reach of visible light, shaping orbits, mergers, and motions. Without them, the cosmic ballet would spin out of control. On the largest scales, dark matter has shaped the universe's architecture. The cosmic web, the immense network of filaments that connect galaxies and clusters across the void, is a map of dark matter's influence. It drew the lines, traced the paths, and pulled matter into place. And yet, we live inside this structure without ever seeing it. Like fish unaware of the current, we move through the tides of unseen mass. Every galaxy's journey, every cluster's dance, every supernova's explosion has occurred in the shadow of this invisible skeleton. Even time, in a way, has been shaped by dark matter. The rate at which the universe expands, the way it slowed and accelerated, the balance between gravity and expansion, all of it depends on how much mass the universe contains, and most of that mass is dark. To remove dark matter from the equation would not just dim the universe, it would unravel it. This is why the search continues, even after decades of effort. It is not just curiosity, it is necessity. To understand dark matter is to understand structure, formation, and the fundamental blueprint of everything we observe. Still, in the quiet moments of wonder, it can feel strange that everything we see is arranged by something we cannot. That light obeys a hidden hand, that we measure the shape of the void by tracing the curves it leaves behind. And if, as you lie in stillness, your thoughts begin to loosen, drifting across these hidden structures, know that your rest, too, unfolds within a universe, quietly held together by what cannot be seen. Let sleep come gently, wrapped in the arms of dark gravity. Even when something cannot be seen, it can still leave fingerprints behind. In modern astrophysics, data is everything. From deep sky surveys to gravitational lensing maps, the universe sends an endless stream of clues. And while dark matter remains invisible, its gravitational echoes ripple through that data, distorting, shifting, guiding. If one looks closely enough, the invisible starts to take shape. Astronomers now use machine learning and powerful algorithms to detect these subtle patterns. They feed telescopic data into simulations, terabytes of galaxy positions, redshifts, velocities, and let the software search for anomalies, not just what's there, but how it behaves, how it clusters, how it moves, how it interacts with light and space. One technique is known as weak lensing. When light from distant galaxies passes through dark matter structures, it bends ever so slightly. The distortion is minimal, almost imperceptible, like looking through a piece of warped glass. But when measured across millions of galaxies, these tiny distortions add up. They reveal the mass distribution along the line of sight, not the visible mass, but the total mass, including dark matter. With enough of these measurements, researchers can construct vast maps of dark matter's gravitational influence. Not a picture of particles, but of presence, a contour drawing in gravity, outlining structures that do not shine. These maps are improving. Telescopes like the Vera Rubin Observatory are poised to gather data on billions of galaxies. Each galaxy, a pinprick of light. Each one, slightly bent by the mass it has passed. With this data, we may one day see the universe not just as it glows, but as it truly weighs. Another powerful method comes from studying the cosmic microwave background, the afterglow of the early universe. The pattern of temperature variations in this radiation contains the faint fingerprints of dark matter, its density, its motion, even its influence on how the universe expanded in its earliest moments. By comparing these patterns to theoretical models, scientists can constrain the properties of dark matter more tightly than ever before. Then there are galaxy surveys, where astronomers measure how galaxies are distributed in space. If dark matter were not present, galaxies would be spaced differently. They would not cluster as they do. The rhythm of their arrangement, the scale at which they gather, matches what one would expect from a universe filled with both dark and visible matter. All of this amounts to indirect detection. But indirect does not mean uncertain. In science, certainty comes not from seeing with eyes, but from coherence. When many different lines of evidence converge on the same conclusion, confidence builds. That's exactly what has happened with dark matter. Rotation curves, lensing, background radiation, galaxy clustering. They all tell the same story. And yet, there's more. Some teams are exploring how dark matter might interact with itself, not with light, not with atoms, but with other dark matter particles. These self-interacting dark matter models could explain why dark matter appears to clump more softly in some regions. If dark matter has even a hint of friction, a trace of resistance, it could help resolve some of the theory's lingering problems. Again, the signs are faint, but the data grows richer every year. This is what science looks like at the edge of the known. Not a sudden revelation, but a slow accumulation. Not a spotlight, but 1,000 candles. And as each new instrument comes online, from space telescopes to underground detectors, the picture continues to sharpen. We are not seeing dark matter directly, but its shadow grows clearer, its weight becomes more undeniable. To listen to the universe is not to wait for a voice. It is to notice the echoes, the bends, the patterns, the silences shaped by gravity. And dark matter, though voiceless, is speaking everywhere. Dark matter is not a single idea. It is a placeholder, a question wrapped in gravity, a name for what we do not yet understand. The standard explanation is that dark matter is made of unknown particles, massive, slow-moving, and largely non-interacting. But what if this framework is only one layer of a much deeper puzzle? As our instruments improve and our theories grow more refined, physicists have begun to wonder, could dark matter be something else entirely? One possibility is that it isn't a particle at all, but a field. In physics, fields are smooth, continuous presences that exist everywhere in space. Think of the electromagnetic field that carries light, or the Higgs field that gives particles their mass. Some theorists have proposed that dark matter might be a field that subtly influences the cosmos, spread evenly across the universe, oscillating slowly, touching everything without revealing itself. A candidate for this type of dark matter is the axion, originally introduced to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. Axions turned out to be a perfect fit for dark matter. If they exist, they would be incredibly light and extremely weakly interacting, yet abundant enough to account for the universe's missing mass. Experiments like ADMX, Axion Dark Matter E-experiment, are now trying to catch the whisper of an axion by converting it into microwave signals in the presence of a magnetic field. So far, results are inconclusive but promising. Then there is the idea that gravity itself might be misleading us. Perhaps our equations are incomplete. Newton's laws work well on Earth. Einstein's general relativity works across solar systems and galaxies. But what if, on cosmic scales, gravity behaves differently than we think? This idea has led to modified gravity theories, attempts to rewrite the rules instead of inventing new substances. One of the most well-known of these is MOND, modified Newtonian dynamics, which adjusts how gravity works at very low accelerations. In some cases, MOND explains galactic rotation curves without invoking dark matter, but it struggles with galaxy clusters and the cosmic microwave background, places where dark matter predictions still perform better. Other modified gravity theories go further, invoking new dimensions, additional forces, or radical redefinitions of space-time itself. Some of these models are elegant, some are wild, but all attempt to address the same persistent question: why does the universe act as if it contains more mass than we can see? There are even more exotic ideas. Primordial black holes, tiny remnants from the early universe, might account for part of the missing mass. So far, searches have turned up empty. Others suggest that dark matter might be connected to extra dimensions, or that it is a shadow from parallel branes in string theory's multidimensional framework. And there's always the unsettling possibility that dark matter isn't a single thing at all, that what we call dark matter might be many different phenomena, overlapping in effect but unrelated in origin. A blend of particles, fields, and perhaps errors in our equations, converging into the same gravitational signature. What keeps physicists going is not certainty, but consistency. The fact that the same gravitational anomalies show up in so many places, the same curves, the same patterns. Whatever dark matter is, it behaves like something real. The theory may be wrong in detail, but something is right in principle. As theoretical work continues, it fuels the experimental side. Each new idea offers a new way to test, to observe, to challenge assumptions. The questions grow bolder, the answers grow stranger, and the universe becomes both more mysterious and more knowable in the same breath. At the edge of theory, everything is provisional, but this is also where discovery lives. Dark matter, whether particle, field, or flaw in gravity, remains the single most pressing mystery of the cosmos, and solving it may require letting go of everything we thought we knew about matter, motion, and the very nature of space itself. The universe, in all its brilliance, may be built more from absence than from presence. We marvel at stars, planets, and nebulae. We map galaxies and measure distances so vast they defy imagination. And yet, all this visible splendor makes up less than 5% of what the universe actually contains. The rest, the vast majority, is hidden. Dark energy makes up the lion's share, but right behind it stands dark matter, the silent scaffolding that holds everything together. It does not burn, it does not shine. It cannot be held, or scattered, or seen with any telescope. But its gravitational grip is everywhere, from the spin of galaxies to the clustering of the cosmos. There is a strange poetry to this, that what matters most is what we do not see, that the shape of everything we love, the stars we wish upon, the galaxies we admire, have all been shaped by something that leaves no mark but motion. Dark matter challenges our senses and our instincts. It cannot be touched or tasted or traced in the ordinary way, and yet it behaves with such consistency, such quiet precision, that its existence becomes hard to doubt. The most profound ideas in physics often begin not with what is, but with what is missing. That is how dark matter entered science in the first place, not as a substance, but as a subtraction. Galaxies rotated too fast, light bent too far, clusters of galaxies clung to each other more tightly than their visible mass could explain, and in each case, the explanation came not from what was there, but from what had to be added to the equation. That addition, ironically, was absence. What we call dark matter is really a way of admitting that the visible universe is incomplete. It is not a theory of fullness, but of insufficiency. This idea resonates far beyond physics. In music, silence shapes the sound. In art, empty space gives form to the figure. In writing, the unspoken gives words their weight. And in the cosmos, it is the unseen that allows the seen to exist as it does. If we could strip away all dark matter, the universe would unravel. Galaxies would drift apart, stars would never have formed. The sky would be empty, not just of light, but of structure. Instead, it is full of order, full of motion, full of echoes from something that does not glow, but guides. For physicists, this is both humbling and exhilarating. It means that our knowledge, though vast, is still partial, that the greatest discoveries may still lie in what we cannot detect, that even now, as technology pushes further into space and deeper into matter, we are still shaped by the mystery of what lies beyond our reach. Dark matter reminds us that knowledge is not the same as vision, that what we understand best may not be what we see, but what we infer. The pull of gravity, the trace of motion, the shape of a curve, they tell a story no eye has ever seen. and that story is still unfolding. We may never catch a dark matter particle in a detector. We may never photograph its shadow or track its trail across the stars. But every time a galaxy spins, or a cluster bends light, or a filament stretches across the void, dark matter is there, silent, constant, and necessary. It is a presence that defines the universe, not by what it gives, but by what it holds together. The universe has always whispered more than it has shouted. In its earliest moments, it expanded not with fire but with silence. No observers, no eyes. Only motion, only gravity, only potential. And among the very first elements of structure was something we still do not fully understand. Dark matter. It has walked beside the visible cosmos since the beginning. We see the light, we map the stars, but behind it all, there is a constant companion, never revealing itself directly, yet always shaping the outcome. A partner in the cosmic dance whose steps cannot be seen, only felt. Dark matter is not just a solution to an equation. It is a fundamental part of the universe's design. It slows the rush of light. It deepens the gravity wells that birth galaxies. It wraps the cosmos in a scaffold of stillness, holding things steady, giving shape to what would otherwise drift into nothing. In a very real sense, we are not just observers of dark matter, we are its result. Without it, the building blocks of life would have scattered, stars would have failed to ignite, planetary systems would have lacked the cohesion to form. Even the heavy elements in our bodies, iron in blood, calcium in bone, owe their presence to stellar furnaces that would not have burned without the help of dark matter's embrace. To understand it, we must embrace paradox, to study what cannot be seen, to map what does not shine, to believe in the weight of silence. And in doing so, we find something beautiful. That the universe, for all its brilliance, depends just as much on what is hidden as what is seen. That the unseen is not the unknowable. That the cosmos can be both illuminated and mysterious, structured and strange. Each time a scientist measures the slow curve of a galaxy's edge, or traces the arcs of light bent around invisible mass, they touch the edge of a deeper truth, that we do not need to see everything to understand it. That wonder can grow even in the dark. And for those who look up at the night sky, not as an endpoint, but as a beginning, it is comforting to know that something vast and silent is holding it all together, not in defiance of the visible, but in support of it. Dark matter is not an intruder. It is the quiet companion that has always been there. So, as the day draws to a close, and your breath softens, and the world dims, let that silence linger. Let the thought rest beside you that even in darkness, the universe is complete. Even in shadows, there is order, and even in sleep, you are held by forces older than stars, present, though never seen. We from Sleepy Stories wish you a good night.